Swayam Prabha. Digital India. Educated India.
Welcome. In the last few lectures, we have been discussing the Rouse model that discusses the diffusion or the Brownian motion of a polymer chain, and so far we have went through a long derivation, and essentially what we have been trying to do is try to replace the positions of beads on the polymer chain by some sort of Rouse modes as variables in the equation, and by doing that what we were able to do is we reduced a partial differential equation that we had into a series of ordinary differential equations which are easier to solve. But more importantly, these Rouse modes have certain physical significance in them, and that is where we ended our discussion in the last class, trying to look at the significance of Rouse modes. So, I will continue the discussion today, and then I will talk about briefly what are the problems the Rouse model has. I already have hinted it earlier, but we will look in more details the problems of Rouse model, and then I will discuss briefly what is known as a Zim model that corrects for those problems and give us the correct scaling behaviors for diffusion coefficient of polymer chain. So, just to recall, what we have been doing is we are looking at the continuous analog of a bead spring model, where we have a contour variable running from n equal to 0 to n equal to capital N, that is the number of segments. In there I have the variable r, that is now a function of n and t, that tells me the position of the beads and segments along the chain, and for that r we started with the partial differential equation like this, which had the boundary conditions for the free ends at n equal to 0 and n equal to capital N. And what we did what I refer to as a linear transformation using what I call the Rouse modes defined by this particular equation. So, earlier we wrote in terms of a basis function, and then using the boundary conditions in the PDE we got the expression for the basis function, that is 1 by n cos p pi n by n integral over r dn. And using that I then have equations of this sort. This was a PDE and this is now a set of ODEs, where P runs from 0, 1, 2 and so on. And then finally we said, of course, we defined the expression for Kp, zeta p and so on, and then we said if I am interested in the center of mass of a polymer chain that characterize the position of the overall polymer chain in space, the center of mass is given by the first or zeroth Rouse mode, that basically characterizes the center of mass, and therefore it characterizes what I refer to as the diffusivity of center of mass or the net overall diffusion of the polymer chain. And then finally we derived that x1 or the first Rouse mode then characterize the time correlation of the end-to-end distance RET. Okay. So, now what do the higher Rouse modes represent in that case? Okay. And it turns out that they have a very clear meaning, and the meaning is the following, that if I have a polymer chain in space, if I divide the chain into two halves along the contour, that is at n equal to n by 2, then if I look at the segment until here, which may have certain end-to-end distance, and the other half that may have certain end-to-end distance, and if I look at the motion of these individual halves, then basically it is characterized by the second Rouse mode. Just like x1 characterize the time correlation of the end-to-end distance, that is for the entire polymer chain, if I divide the chain into two halves, then these individual chains do have a local motion, and the local motion is of the two halves is given by x2 t, the second Rouse mode. Okay. Similarly, if I now divide the chain into three halves, and I am using a different color again. So, let me divide the chain into three parts. So, we will have divisions at n by 3, 2n by 3 and so on. So, we now have three polymer chains or three segments, and then for these three halves the local motion or 3/1/3 are given by x3t. Okay. So, if I extend this kind of logic, then xpt characterizes the local motion of a chain of n by p segments. So, there would be p such chains in a given chain, or p such segments, p such chains containing n by p segments each within the polymer chain, and the local motion of those sub chains are given by the Rouse modes xpt. So, using this idea, if you can see that as I go to higher and higher Rouse mode, or as I am increasing the value of P, I am essentially looking at a more localized motion within the polymer chain. Very high values of P characterizes very local motions, let us say between 2 beads or 3 beads, and the lower values of Rouse mode, the lower values of P correspond to the motion of relatively larger chains, and in fact x0 characterize the center of mass of the overall chain. Okay. So, therefore, not only the idea of Rouse modes basically is helpful to reduce the partial differential equation into ordinary differential equation, what is more important is that they actually characterize the motion of polymer chain at different levels. Okay. So, this is not really a one-to-one transformation. We do not directly write R and T as some kind of a one-to-one mapping to some x t variables. This is not the case. On the other hand, what we are doing is we represent these different Rouse modes as a linear transformation over R given by that particular function, and it then characterizes the motion at different length scales that we would see in a polymer chain. Okay. So, that is where this whole idea become very important, and in experimental literature you will find descriptions of the sort the motion at second Rouse mode, third Rouse mode, depending on what kind of experimental resolution do I have, I would be able to see motion at different length scales. And if I am really zooming in, I am basically looking at higher xp value, xp for larger p. If I am zooming out, I am looking at lower xp or lower values of p in the thing, and in that sense the xp completely characterize the chain motion at all sorts of length scale. Okay. So, there is a couple of problems with the Rouse models, and the most important problem is if I look at the net diffusivity within the Rouse model, we find that it scales like 1 by n, that is, if I increase the number of segments, the diffusivity decreases. This is although correct at a qualitative level, this is what does happen in a system. The larger polymer chains will have lower overall diffusivity. They may have a high degree of local motion, but the overall diffusion or the overall motion of center of mass would be lesser if the chain has a larger value of n. But it turns out that the scaling is not quite correct. The scaling experimentally is found to be something like 1 by n nu, where nu happens to be the same scaling coefficient that we had got for the Re or the Rg, as we were doing in the very beginning of the class of the course, that we obtained certain scaling for Re and Rg using random walk models, and they were of course different in a good solvent and a bad solvent and a theta solvent regimes. Those scaling laws do appear again in diffusivity, and this is what is referred to as a dynamical scaling. And what we had earlier is referred as static scaling. This particular result comes out to be somewhat surprising to begin with, because on one hand Rg is a quantifier of a length and d is a quantifier of some kind of a motion of a polymer chain. So, the reason the thing that we get the same scaling law for both of them is somewhat surprising. However, keep in mind that both of them represents the equilibrium behavior. Nowhere in here we have assumed that we have departed from equilibrium. This is like referring to the Brownian motion that is taking place at equilibrium. So, since both of them refer to equilibrium properties, it turns out that the scaling behavior is identical to what we get in the case of the end-to-end distance and so on. Okay. Now, the only thing is that we do not get the correct scaling law if I am doing the Rouse model. It is at qualitative level it is correct, but it is not giving us the correct value of scaling exponent. So, the reason why it fails is because we have made an assumption in what we have done so far, and the assumption is that we have the bead as a free particle that is only experiencing an external force because of the presence of other beads in the system, but it is not affected by, for example, other polymer chains in the system, and the spring force is the only external force that is acting on the system. What really happens is that the force acting on a bead also in turn affects the force acting on the other beads, and this is what is referred to as hydrodynamic interactions. Okay? And if I include those interactions in the model, this is what is called a ZIM model. So, we will first discuss what do we mean by hydrodynamic interactions, and then we go on to discuss the ZIM model of a polymer solution. So, before I get there, I must tell you that even though the Rouse model is nowhere in derivation we have assumed that it is a polymer solution or a melt, we are looking at a single polymer chain. It turns out that the Rouse model do work for the case of a polymer melt for the reason I am not going to detail, but it gives you correct scaling for the polymer melt systems. It does not work for dilute polymer solutions or even what is known as a semi-dilute polymer solution. Okay. So, let us now try to set the ground for the ZIM model by discussing what is known as hydrodynamic interactions. And before I do this for a polymer chain, I am just doing it for a system containing more than one Brownian particle. What we have earlier discussed was a Brownian motion of a free particle, that is just one particle in a solution, and now we want to do for more than one particle. We see like what does happen in that case, and then we extend the idea to a polymer solution. So, let us say that now in a system we do not have just one particle, we have more than one particle. Okay? So, this can be, for example, a case of a suspension that contains more than one particle. If they are connected, they would form a polymer chain, but let us not get into that at a moment. Then if, for example, in this particular bead right here, let us call it the bead N, we apply a force Fn, or the force is applied due to some external field present in the system, as we will soon do for a spring force in the case of a polymer chain. Let us say a force is applied there due to whatever reason, then this force will basically lead to the movement of this particular bead. Now, once the bead moves in a solvent, it does affect the flow field around it. Okay. So, all the other beads in the system would see a flow field that is created by the movement of this particular bead. Think of like as a analogy, think of like fishes in water. If say one fish starts moving in water, the water around the fish will develop a flow field, and other fishes will also see the same flow field. Okay. So, the motion of one fish do cause a change in the flow field, and those changes must be then affecting the motion of other fishes. Of course, this is a very distant example, but it serves the idea. Similarly, all the other beads, let us say the bead M here, this bead also is moving due to the external force or whatever force acting on it. That bead is also giving rise to a flow field, and then bead N here, the black one, the filled one, also is affected by the flow field created by M. Okay. So, in totality, all the beads in the system are experiencing different forces or maybe same force, but all the beads are contributing to the flow field that is present in the system. It is not that the flow field is given and all the beads are simply responding to that flow field. All the beads are themselves responsible for the flow field that is present in the system, and therefore, the velocity or the motion of each of the beads are coupled with the other beads. Okay. This is what is referred as a hydrodynamic interaction. It is more pronounced if the size of the bead is larger. It is less pronounced when the size is smaller. In a limit, when we have very dilute solution and size are smaller, we can ignore this effect, but it turns out that that limit is seldom reached. In most systems, the effect of hydrodynamic interactions are quite significant, and they must be included for a proper description of the system. So, now in general, if I am looking at the velocity of the nth bead, it must be related to the velocity of the mth bead, and in fact, it must be related to all possible values of m. That is, we must sum over all the m values going from all beads, and the coefficient of that relation is what is known as a mobility tensor. So, it must be a tensor because tensor dotted with a vector would give you a vector. This quantity is called a mobility matrix. Okay. So, in very dilute solutions, so there is small correction here. Actually, the relation is not with the velocity, but the relation is actually with the forces that are applying on each of the beads, and eventually the forces are what is giving rise to the velocities. So, velocity of any particular bead in the solution is affected by the forces acting on different beads. Of course, the velocities also have to be related, but that will come from this relation. We are essentially relating the velocity to the forces acting on different beads. So, in a very dilute solution, it turns out that I can write the mobility matrix as something like an identity tensor delta n m by zeta, where zeta is the drag coefficient that we have discussed earlier, or friction coefficient. This is a matrix that has ones along diagonal and zeros everywhere. What that means is, if I look at the alpha beta component of this mobility matrix, that would be delta alpha beta. The chronicle delta will represent the identity tensor, because for alpha equal to beta we have diagonal terms which are 1, and alpha not equal to beta we have off diagonal terms which are 0, multiplied by delta Nm by zeta, and therefore we can write V n alpha as H n m alpha beta F m beta, using the relation that we had here, where we are summing over all the values of m, which gives me delta alpha beta delta Nm by zeta F m beta, which then give rise to, it is only true for, only non-zero for n equal to m, that is one thing, and it is only non-zero for alpha equal to beta. So, what do we get is essentially simply f n by zeta, which is similar to the expression that we have used to discuss the Brownian motion of a free particle. Okay. Here we have not explicitly put a random force term, but the idea remains there that if I really go to a very dilute limit, then the velocity of a bead is only affected by the forces acting on the bead. The bead will not see other beads. Of course, they will have a flow field around it, but that flow field will not affect it. Assume that there are only, say, 2 fishes in a very large pond, and if the fishes are far away, they are of course swimming there, they have certain flow field wherever they are swimming, but that flow field is not affecting the flow field of a fish here. The fish is moving here because of the forces acting on this, the fish is moving there because of force acting on this. Only when the 2 fishes come close enough, their force fields, their flow fields will affect each other, and then we can say that whatever force I apply on this fish will also affect the velocity of that fish that we have. Okay. So, only in a very somewhat less dilute solution, when the beads are relatively close together, we can start having this hydrodynamic interaction, and it turns out that we don't really need to very dilute, we don't need to go to a concentrated case. It already starts appearing for relatively more relatively dilute cases that we have in physical circumstances. Okay. So, with this idea, now the objective we have is, how do I get that flow field? So, we want to know that how the flow field is created in the solution because of forces present on the beads. Okay. So, we have to solve for the velocities, and we know from fluid mechanics that to solve for velocities we have to go to Navier-Stokes equation. It turns out that since we are interested in motion close to equilibrium or motion at equilibrium, we don't really need to go to a large Reynolds number, because of course turbulent flow is far from equilibrium. We actually can go to a very low Reynolds number, and there we have what is known as an Stokes equation, and that is what can be used to get the flow field that we are interested in. So, we will start from this point in the next lecture, and try to derive the expression for this velocity, and using that we will derive what is known as the GIM model of polymer solutions. With that I conclude here. Thank you.